All right, let's get right into it. Google just made a huge splash with their new quantum processor, Willow. And really, the big question for us today is this. Is this the moment quantum computing stops being just a cool science project and turns into a legitimate, investable thesis?
I mean, seriously, what if that fuzzy, kind of far-off promise of quantum advantage suddenly got a hard number attached to it? A result you can actually verify and maybe even a clear path forward.
Welcome to the chip market. Our job is to cut through all that noise and give you the real signal on what stuff like Google's Willow chip means for computing and, more importantly, for your money. So first things first, what is Willow? Let's forget the hype for just a minute and talk about the actual hardware. What did Google's engineers build?
Okay, so the headline number for the chip is 105 qubits. It's a superconducting processor. Now, as investors, we know that the qubit count is what grabs the headlines, right? But we also know it's only a tiny, tiny part of the story. The real magic, the secret sauce, is in the quality of those qubits.
And wow, this is where Willow really starts to flex its muscles. I mean, look at these fidelity numbers. We are talking 99.97% on single qubit gates, almost 99.9% on 2-qubit gates. At this scale, those are absolutely best-in-class figures. And check out the coherence times. That's how long the quantum state actually lasts before it poofs into nothing. Willow is 3 to 5 times better than Sycamore, its predecessor. This isn't just a little step up. It is a serious leap in hardware quality.
And that performance, well, that allowed Google to claim something totally new. And for us, something much more concrete. We're not just talking about quantum supremacy anymore. The new phrase is verifiable quantum advantage. So let's break down what that actually means, because it's important.
The key word, the most important word on this slide, is verifiable. See, this isn't about solving some weird abstract problem where you can't even check the answer. This means Google ran a task, they got a result, and they are claiming that any other quantum computer of the same caliber could run the exact same experiment and get the exact same answer. It's repeatable, it's testable, that's a game changer.
And the performance gap they're talking about, it's just staggering. They're claiming a 13,000 times speed up over the fastest classical methods we know of.
To put that number into perspective, let's look at the actual task. It's called quantum echoes, and you can think of it as a really complex physics simulation that's actually pretty relevant to chemistry. Willow crunched through it in just over 2 hours. The estimate for the world's fastest supercomputer to do the same job? Over 3 years. Yeah, suddenly that theoretical speed-up becomes very, very real.
And this quote from Google just hammers the point home. Verifiability is the new gold standard. It shifts the entire conversation. We're no longer asking, hey, did you do something a classical computer can't? Now the question is, did you get a reliable answer to a problem faster than a classical computer could?
So does this mean Google just won the quantum race? Is it game over? No way. Not even close. This milestone is huge, for sure, but it's happening inside a brutally competitive landscape where different players are betting on completely different kinds of technology.
So let's do a quick market map. You've got Google and IBM slugging it out with these superconducting qubits. Then you've got a company like IonQ using something called trapped ions, which gives them this amazing all-to-all connectivity. And then there's D-Wave, which is kind of in its own lane, using thousands of qubits for a really specialized thing called quantum annealing.
And here's the crucial point for any investor. There is no single best technology yet, not by a long shot. Every single one of these approaches has fundamental trade-offs. Google's superconducting chips, they're wicked fast, but they're also really sensitive to noise and errors. IonQ's trapped ions, they're incredibly precise, super stable, but their operations are much, much slower. The winning horse in this race is still very much up for debate.
Okay, so what does all this actually mean for us as investors? How do you even begin to position your portfolio for this kind of technological arms race where the winner is completely unknown?
Well, one of the most prudent strategies is to think about it with a core and satellite approach. So the core of your portfolio, say 70%, could be in the big established players, the hyperscalers like Google, and the critical semicap equipment companies that supply everybody. Then your satellite positions, that other 30%, that's where you can take on some more risk with the pure play quantum companies that have that higher reward potential.
And you know, a smart investor never forgets about the supply chain. The companies building the picks and shovels for this quantum gold rush are a massive part of the story. We're talking about companies that make advanced cryogenics to keep these chips at near absolute zero.
Specialized control electronics like FPGAs and DACs, the folks who produce the high-purity materials. It's a whole ecosystem.
All right, so looking ahead, if we're going to track this space intelligently, what are the key signposts? What should we be watching for on the horizon?
First, let's just manage our expectations with the realistic timeline. We are right here in 2025 at this verifiable advantage milestone. This is still what we call the NISQ era. That stands for Noisy Intermediate Scale Quantum, and the noisy part is key. These machines still make a lot of errors. The next big step? Demonstrating the very first error-corrected or logical gates. That might be a few years away. And truly useful, fault-tolerant quantum computing? We are probably looking at 2035, maybe even beyond. This is a long game.
So, here it is, your simple quarterly KPI dashboard. Here are the questions you should be asking. Number 1. Are companies making progress on logical, error-corrected qubits? Stop focusing on the physical count. 2. Is gate fidelity getting better across the industry? Is that error rate consistently dropping? 3. Are real companies with real budgets starting to pay for access to these machines? And 4, and this is a crucial one, how are classical computers catching up? Because they are a constantly moving target.
And that really leaves us with the final question to chew on. Google's milestone is without a doubt a massive leap forward, but the goalpost for what quantum advantage means will just keep moving as classical computers get better and better. So, as an investor, you have to decide, are you betting on a single breakthrough technology, or are you investing in the infrastructure and the key players that are going to fight it out in a decade-long arms race? That's our breakdown for today. If you found this analysis useful, do us a favor and hit that like button, drop your thoughts in the comments, and of course, subscribe for more deep dives into the semiconductor world. Thanks for watching.